Now that we know a little bit about linear transformations, we want to realize that we can actually do operations with transformations. And in this video, we're going to talk about how to add together multiple linear transformations and how to scale a linear transformation. So the first thing we want to recognize is that if we have two transformations, so we've been using the letter T, capital T, to represent a transformation. So let's go ahead and call these two transformations capital S and capital T. In order to add linear transformations, both of the transformations have to transform from the same space to the same space. In other words, if I'm transforming for S from Rn space to Rm space, regardless of the values of n and m, that means that the transformation T also has to start in Rn space and transform to Rm space. In other words, I have to have matches. These two values here have to match, and these two values here have to match. So if S transforms from R2 to R3, T also has to transform from R2 to R3. So as long as those two match, then I can actually add S and T together. So the first thing that we want to remember is that any linear transformation can be written as a matrix vector product. So let's say I have the transformation S, and I go ahead and write it as the matrix A multiplied by the vector X. That's how I express the linear transformation S. And then let's say we write T as the transformation matrix B multiplied by the vector X. So we turn S and T into their matrix vector products. Of course, when we do that, the dimensions of A and B will match. So we'll go ahead and say that A is an m by n matrix, and that B is also an m by n matrix. If all this is the case, then I can go ahead and add the two transformations. So the sum of S and T, we could write this way. We could say the sum of S and T of the vector X. In other words, when I take the transformation of X using the sum of the two transformations, that's the same thing as taking the sums of the individual transformations. So S of X plus T of X. In other words, if I'm trying to transform a vector X, I can transform X using T, and then I can transform X using S, and the results of the two of those I can add together, and that's going to be the same thing as first adding the transformations to get one transformation matrix, and then applying that one transformation matrix to the vector X. So in other words, I can see that when I rewrite these transformations as their matrix vector products, because I can write S of X as A times X, the matrix A times X, and I can rewrite the transformation T of X as B, the matrix B times the vector X. And then I know that this kind of matrix addition is distributive, so I can rewrite this as A plus B times the vector X. So this is telling me here that if I write S as a matrix vector product and I express the transformation T as its transformation matrix B, then in order to find the sum of the transformations, I just add those two transformation matrices together, and then I can apply that single transformation matrix to X. So let's say, for instance, that the transformation S rotates every vector around the origin in R2 space by 90 degrees. Well, we looked at that when we talked about rotations. We could then write the transformation S as its matrix vector product, and we know that the matrix that rotates vectors 90 degrees around the origin is the matrix 0, -1, 1, and 0. And then let's say that the transformation T, so we'll say when we apply the transformation T to a vector X, what does it do? Well, let's maybe say it stretches horizontally by a factor of 2. That means that we would have here 2, 0. Because remember, the first column of a transformation tells you what happens to the standard basis vector I. The standard basis vector is the vector 1, 0. So if I want to stretch 1, 0 horizontally by a factor of 2, that means I just multiply it by 2, so this becomes 2, 0. And let's say T also stretches vertically by a factor of 3. Well, that means that I'm stretching the standard basis vector j, which is the vector 0, 1, by a factor of 3, and so my result there is 0, 3. And now I want to add these transformations together. So normally what I would have done, let's say I want to transform the vector 1, 1. So I'm going to say that my vector x is the vector 1, 1. We know that we can do this. We know that we can add the transformations together. And what we saw here is that all we actually need to do is add the matrices together to get one transformation matrix that encompasses all of these, and then we apply that to the vector x. So when we add the matrices, let's go ahead and put this 2, 0, 0, 3 up here so that we can add these. So the sum then will be 0 plus 2 is 2, negative 1 plus 0 is a negative 1, 1 plus 0 is 1, and 0 plus 3 is 3. So this will be my transformation matrix. It's the sum of the two transformations. And now I can just apply this to the vector 1, 1. So I can just take the sum 2, negative 1, 1, 3, and multiply it by the vector 1, 1 that I want to transform. And the result there will be 2 and a negative 1 is 1, 1 and 3 is 4. And so after adding those two transformations together, the result is the vector 1, 4. So this was what we got when we looked at adding the transformations. Now we want to talk about scaling a single transformation. And scaling a transformation is equally simple. We'll use the transformation t. So let's say we have t of the vector x. If we want to multiply that transformation by some scalar, which we'll call c, then what we want to realize is that we can write the transformation t as its matrix vector product. So remember over here we said that the transformation t could be written as the matrix vector product b times the vector x. So this then becomes c times b times the vector x. And what we want to realize is that this is really the same thing as c times b times the vector x written this way. In other words, I can just take that transformation matrix, I can multiply it by the scalar, and then I'll end up with the resulting transformation matrix that I can just apply to the vector x. So let's say we use that same transformation t, because we have t of x here. When we rewrite the transformation as its matrix vector product, we use this matrix here, and we say that this is equal to c times our matrix 2, 0, 0, 3 times any vector x that we want to transform. And we just want to realize here that we can apply c to the matrix first. So let's say that we want to scale up this transformation by negative 2. So we'll say that c is negative 2. And then the result here will just be us applying negative 2 to every entry in the transformation matrix. So we'll get negative 4, 0, 0, and negative 6. And then we'll apply that to any vector that we want to. So let's say we want to apply this to, again, the vector 1, 1. We'll just take our transformation matrix that we've already scaled up, and we'll multiply that by the vector 1, 1 that we want to transform. And when we do that, we'll get negative 4 and 0 is a negative 4, and 0 and a negative 6 is a negative 6. And so what this tells us is that when we multiply the scaled transformation by the vector 1, 1, we get the transformed vector negative 4, negative 6. So we just want to remember that when it comes to linear transformations, if we have a linear transformation, and you know you've got a linear transformation if it can be written as a matrix vector product, then we are able to add linear transformations and scale linear transformations by adding and scaling those matrix vector products.